Chapter 10 is going to deal with energy and thermodynamics. We're going to take a look today at a lecture dealing with the nature of energy, temperature and heat, and endo and exothermic processes. So let's start with the nature of energy. Energy is the ability to do work or to produce heat. That's just the definition. It's that which is needed to oppose natural attractions, and this law is an important law for you to know. This is the law of conservation of energy, and it is exactly what it says it is. Its energy can be converted from one form to another, but can be neither created nor destroyed. And the total energy content in the universe is said to remain constant, so we don't lose it. Potential energy is the energy due to position or composition, so this is the stored form of energy. Kinetic energy, on the other hand, is energy due to motion of the object, and it depends on the mass, which is where M comes in, and the velocity of the object, or how fast it is moving. And so kinetic energy is 1/2 mass times velocity squared. So let's look at this initial position picture. So this is saying we have ball A and we have ball B. And ball A has a higher potential energy because it has a higher level of, let's draw this line right here. It's located right here, while ball B is located down here. So it has a higher position. This higher position allows it to have more potential and a higher amount of potential energy than ball B. So let's see what happens when he lets go of ball A. And that energy that was stored up here, the potential energy in ball A, has rolled down and it has hit ball B and caused ball B to move. So it's rolled down the hill. The potential energy that it had is lost because it's been converted to random motion of the components of the hill. So it's energy, it's a frictional heating that happened as it went down this hill, and it increased the potential energy of ball B. So that energy being transferred, ball B is at rest and has more potential energy than it did down here. We're going to take a look at energy a little bit more. The first bullet says heat involves the transfer of energy between two objects due to a temperature difference. So by definition, that's what heat actually is a difference of energy between two objects due to a difference in temperature. Work is, by definition, force acting over a distance. A new concept that's going to be a little difficult to pick up on at first. Energy is what we call a state function. And a state function we're going to get into. Work and heat are not examples of a state function. So let's look at what a state function is by definition. A state function says that property does not depend on it in any way on the system's past or future. It only depends on the present state. It is a property of energy, and it changes independently of its pathway. And I know that's just by definition, so let's take a look and try to make sense of what a state function actually is. So, state functions. Distance traveled from one location to another, is that a state function? It's not, because that depends on the route that you take. So I could go from here to Deloge, and I could take 8 highway, or I could go from here to Deloge, and I could go through Ludwood, and I could take the old highway. So I'm still going from here to Deloge, but I have different routes. So since the distance traveled from one location to another could vary depending on the route taken, it is not considered to be a state function. What about changes in elevation? It is a state function because the change in elevation is always the same. It doesn't depend on the route taken at all. So if I go from here to Colorado, you know there's a big difference in elevation between St. Louis and between Denver, Colorado. It doesn't matter how I get to Denver from St. Louis. That's not a state function because the distance could be different. I could drive in circles if I wanted to. However, when I get to Denver, there's a definite difference between where St. Louis is here, and here's the arch in St. Louis, and how high up it is compared to Denver up here in the mountains. So this difference between here and here is a state function because it doesn't matter what route I take to get from point A to point B, the elevation itself is always going to be the same. Let's look at the definition of temperature. A measure of the random motion of the components of a substance. So hot water has a temperature of 90 degrees in this case, and that is the measure of the motion between the molecules. Cold water at 10 degrees, then if you notice the little jet trails here behind the water molecules at 10 degrees compared to the one at 90 degrees, this temperature is is less, and that means that the motion is slower within those components. So when we look at the temperature, we're measuring the random motion of the components, and the hotter the temperature, the faster, the higher the random motion, which means a higher temperature, and vice versa. Let's look at the definition of heat. A flow of energy between two objects due to a temperature difference between the objects. So heat's the way in which thermal energy is transferred from a hot object to a colder object. So we have a hot object here, so hot water at 90 degrees, cold water at 10 degrees. And what is happening after a while is that this heat from the hot water is transferred to the cold water, and they eventually, over time, will end up at an average of those two in this case, and eventually they'll be at 50 degrees Celsius as opposed to 90 and 10. And that's due to the flow of energy between the two objects. So going on to exo and endothermic processes, we need to have a couple of definitions set in our minds. And so we're going to look at what a system is compared to what the surroundings are. So a system in our area of chemistry is the part of the universe where we're going to focus our attention. And the surroundings are going to be everything else outside of that in the universe. So the system is the part that we're focusing attention on, surroundings is everything else. All right, let's take a minute to look at exothermic and endothermic processes. So if you'll notice, this is just a match, and we have a match up here, and we have to strike it on the box in order to burn the match. So the potential energy is highest here when the match is the reactant. In this case, the system is the match, and the surroundings are everything else. Once we strike the match and the match is burned, the potential energy in the match is given off as kinetic energy, and it's released as heat to the surroundings. And when we get finished, our product is the match that's already burned up, and we can't get that back in this case. So our reactant has a higher potential energy than the products. Now that we have looked at the movement of energy change when we do something common like it's burning a match, let's look at the definitions of what an exothermic and an endothermic process actually are. So by definition, again, endothermic, endo means into, so heat is going to flow into a system. It's going to be an absorption process, and it's going to absorb energy from the surroundings in an endothermic reaction, where exothermic is going to be just the opposite. Energy flows out of the system, and the energy gained by the surroundings must be equal to the energy that's been lost by the system. So let's look back at the slide before it and determine if this is an exothermic or an endothermic process. Well, energy is released to the surroundings, and the potential energy goes from a high to a low. So the system released energy to its surroundings. So let's look at our definitions on the slide we just got finished with. In an endothermic process, the heat flows into a system and absorbs energy from the surroundings. Is that what's going on in this picture? Are we having heat flow into the system? Well, the heat's not flowing into the system, it's flowing out of the system into the surroundings. So instead of being an endothermic process, this is an exothermic process, which should make sense because it gives off heat, and you notice that when you light a match. So energy flows out of the system, and the energy gained by the surroundings has to be equal to the energy lost. One of the things I want you to do when you look at this picture, though, is pay attention to how they have listed as reactants and the products. So in an exothermic reaction, let's just write that across here, XO, out in heat, the reactants have a higher potential energy than the products. And in an endothermic reaction, we're going to see just the opposite because energy is going to go into the system. So our reactants are actually going to have a lower potential energy than what our products have because energy is going in, so the products will have a higher potential energy. This can be a confusing concept, but if you focus on this picture and think about what's actually going on with lighting this match and reverse it for an endothermic reaction where energy is going to go into the system from the surroundings, it will make a whole lot more sense. Okay, so we're going to look at a concept check, and it's an interesting question to think about. So, is the freezing of water endothermic or exothermic? Freezing of water, going from a warm substance to a colder substance. And while you'd want to lean toward endothermic because it gets colder, what you have to remember is that it's an exothermic process. you have to take energy out in order to slow the molecules down to form the solid. So it's considered exothermic. Okay, let's look at some more examples. So we're going to classify each of these processes as being exothermic or endothermic, and we're going to talk about an explanation for each one of these. So your hand gets cold when you touch ice. Is that an endothermic or an exothermic reaction for your hand? It gets cold when you touch ice. The correct answer is exothermic because heat energy leaves your hand and moves into the ice. So when we're talking about your hand, heat's going to leave it and go to the ice. It's an exothermic reaction. Let's look at another example. The ice gets warmer when you touch it. So the ice, is it going to be considered exothermic process or an endothermic process because the ice gets warmer? The answer is endothermic because heat energy flows into the ice. What about water boiling on the stove? Is that an endothermic or an exothermic? That is an endothermic reaction because heat energy flows into the water, which allows it to change states to boil. What about water vapor condensing on a cold pipe? So you have water from the air becoming liquid from a gaseous state. Is that endo or exothermic? And that's exothermic because the heat energy leaves to condense the water from gas to a liquid. So energy has to leave the system, so it's exothermic. Okay, so let's look at the last example, ice cream melting. Is that endo or exothermic? Well, it's going to fall in the same category as the water boiling and the ice getting warmer. If the ice gets warmer when you touch it, it's endothermic. If ice cream melts, it again is also going to be endothermic. All right, let's look at this next concept check. For each of the following, we're going to define the system, we're going to find its surroundings, and we're going to define the direction of energy transfer. Okay, what about methane burning in a Bunsen burner inside a laboratory? Okay, so first of all, we're going to look at it and know automatically this is an exothermic reaction, and it's exothermic because we're giving off heat to the surroundings. So what are the surroundings? Everything else except for the methane burning. So in this case, the system is going to be the methane and the oxygen that are burning to produce the carbon dioxide and water. Everything else is considered the surrounding. Let's look at the next example. Water drops sitting on your skin after swimming and they evaporate. Is this endothermic or is this exothermic? Let's identify the system first. So in this case, the system is going to be the water drops that are sitting on your hand. Okay? Everything else is considered the surroundings. So is it endothermic or is it exothermic? Well, in this case, we have evaporation going on. In order for water drops to change from liquid to gas, energy has to be put into it in order to allow evaporation to occur, and because of that, it's considered an endothermic process. And I know these seem kind of confusing, but the more that you do and the more that you think through what actually exo and endothermic mean, the easier it's going to become. The last concept check we're going to look at for this section asked if we have hydrogen gas and oxygen gas and it reacts violently to form water, which is lower in energy, the mixture of hydrogen and oxygen gases or the water. So let's kind of draw it out here just a little bit. You know how good of an artist I am, so we might as well put my skills to use, right? Okay, so we have hydrogen gas and we have oxygen gas, and we're going to produce water. And it tells us right here that the mixture of hydrogen and oxygen gases are going to react violently. So what does it mean in the reaction if it's going to react violently? Well, that means that there's going to be an extreme amount of energy given off. And this energy that's given off is given off to the surroundings. So where are we going to see the higher amount of energy? In the reactants or in the product? And it's obviously going to be in the reactants. And the reason for that is because they reacted and gave off energy to the surroundings. So the energy is higher in the reactants and it's going to be lower in the products. So when we look at this, the lower amount of energy will be in the water or in the products. And this corresponds to the picture that we had, the diagram we had with the match being lit. So that's another example you can go back to and apply to that drawing. So let's look at some of the problems that you're going to be able to do for this section.